Right. Yeah, thanks so much, Atsu, for inviting me. I'm happy to be here. So my name is Dariel. I'm a fourth-year grad student at Caltech, advised by John Prescue. And today I will share a bit about our work on this universality of Scrooge ensembles in quantum manifold systems. And this is a recent work that was done with my awesome collaborators, Tobias from TII Abu Dhabi, Wenwei Ho from NUS Singapore, and my advisor, John Prescue. So before I start talking about Scrooge ensembles and how that's related to quantum manifold systems, one of the key motivations for us in this work is to go back to this fundamental question, which is what is a quantum chaos, particularly in the context of many-body systems. And well, the short answer is that I have no idea. And this is a question that's been open for a long time, and it's even though it's so intuitive, sometimes it's hard to define this very clearly. But nonetheless, over the years, people have worked out several ways to characterize quantum chaos through certain diagnostics. So perhaps one of the more popular ones is through the use of random matrix theory, where one could show that quantum chaotic systems generally exhibit some kind of properties that are reminiscent of what we get from random systems. In terms of something that's more physical, they also exhibit physical phenomena such as thermalization. So even though many body states are pure and do not are generally evolving under closed system dynamics, they can be locally described by Gibbs states, which represent the connection between quantum mechanics and thermodynamics. And in some sense, a more modern take is through these ideas of quantum information scrambling, where quantum information that is originally local quickly becomes scrambled into non-local degrees of freedom through this chaotic dynamics. And one of the features about quantum systems in these different settings is that they exhibit what's known as universality, which means that different systems, even though they have different microscopic details, can still exhibit the same features with respect to these diagnostics. So one way to sort of capture the essence of all these features of quantum chaos is through what is known as the projected ensemble, or sometimes it's also known as a snapshot of a quantum system. So let me try to explain this protocol. It's actually pretty simple. So typically one would start with a many-body states, psi, which is supported on a bipartite system, A and B. And this system evolves under some ergodic or chaotic dynamics and becomes scrambled, after which subsystem B is measured in a simple basis, such as the computational basis. And what happens is that for each measurement outcome, this would project the remaining unmeasured system into some pure state psi that's labeled by the measurement outcome. So if you do this repeatedly for every measurement outcome, you get a pure state. And after repeating this for many rounds, you would obtain a distribution of pure states that's supported on A, conditioned on the measurement outcome of B. So this was an idea that was proposed by Kotler et al. In 2023 and experimentally studied in a recent paper. And what this tells us is that the projected ensemble, in this sense, captures some microscopic details about the system psi. But however, because you can see that from the form of this projected ensemble, it contains almost all the information about the original state. So it becomes very hard to analyze properties of the projected ensemble just by studying it full. So one useful way of understanding the universal structures that arise in projected ensemble is to look at sort of a coarse-grained viewpoint, where we study this statistical moment. So here the moments are defined similar to how one would define a density operator. So we would look at the projected state psi, and we will average it over the distributions of the measurement outcomes. The sort of modification is that here we are taking k copies of each projected state. So in this definition, if you look at the case of k equals to 1, that just corresponds to the density operator acting on A. So having access to higher k essentially allows us to probe universal fluctuations in these projected ensembles, and that allows us to sort of understand this higher order properties of the systems. Okay, so before I tell you about what we understand about the nature of this projected ensemble, here's a very useful sort of reference ensemble that one typically studies. So I want to
Sorry,
take a yes.
can I quickly ask this question? So,
Mhm.
so this row K that you've written here,
Yeah.
is it clear how one obtains this experimentally? Because I guess if you measure it with some probability, you would get Z, and then maybe you don't look at Z and you look at the distribution. But how do you get multiple copies for the same Z? Is that clear?
Yeah. So if you want to see this, yeah, typically if you want to prepare k copies of this state, you have to post-select on the same outcome, right?
Mhm.
Um, so one sort of course, that is exponentially costly. So this
Exactly.
is similar to how one would do, let's say, cross entropy benchmark. You would typically rely on classical simulation in order to sort of access this multi-copy properties, right? So you would measure um, you will measure one copy through the experiments, and then you would do, based on the measurement outcomes, you do a classical simulation to get this higher order property. So um, yeah, but to get
And
it
how
directly
should I
from the
think
experiment.
about it?
Mhm.
Like, how should I think about it physically? Like this, is this object is it a physical object, or like how should I think about this? This row K object?
Yeah, so this row K here, it's essentially characterizing, well, it's a physical object in the sense that it's a density operator, but now instead
Yeah.
of living on the original Hilbert space on A, it lives on the symmetric subspace of this K copy Hilbert space.
Okay. Thank you.
Yeah. So this object row K here, yeah, that's a great question. So this object row K here is it's also studied in a more familiar context in quantum information theory, and one of the places that it shows up is in this idea of quantum state designs, which I'll now describe. So, as we know, Haar-random states are a very nice toy model of an ensemble that describes uniform distributions of pure states on the many-body Hilbert space. And these are very useful in many contexts, such as quantum information theory for benchmarking and learning applications, and also in understanding fundamental physics, such as black hole dynamics. Now, however, the quantum complexity of Haar-random states are typically exponential in the system size. So if you ask what's the circuit depth required to prepare a typical instance of a Haar-random state, then one would find that this requires a depth that grows exponential with the number of qubits. So to sort of get the advantages of Haar-random properties and with a complexity that's not exponential, what people um, define or what people study are sort of approximations of that, known as K designs, where instead of reproducing all the properties of Haar-random states, you would demand that they approximate only the low moments of this Haar distribution. So more specifically, if you look at this cave moments um, of a state that's drawn from an ensemble, um, so if it's a K design, if it is matching the cave moments of the Haar ensemble up to some small error epsilon. So this small error epsilon here, you can think of this as a small operator with a trace norm that is bounded by epsilon. Right. So maybe I'll recap some basic properties of K designs, and these are things that are quite well established in the literature. So firstly, by definition of being a K design, this means that any quantum experiment that utilizes K copies of this states cannot distinguish these designs from Haar-random states. And secondly, any K design is automatically a K prime design for any K prime that's smaller than K. And you can see this just by um, tracing out copies of this state psi, such that we are using K prime copies. Now, one sort of very interesting fact about K designs is that even though they are trying to mimic the behavior of Haar-random states, which are very complex, it turns out that for K smaller than equals to 3, this can be classically simulated efficiently. And sort of the most famous example is this stabilizer states, which are themselves approximations of Haar-random states up to the third moment. Now for higher k that it's greater than 3, it turns out that there's an efficient way to generate them in a quantum setup through local random circuits. So this was a sort of well-known result that the circuit depth required to prepare k designs only scales polynomially in the number of qubits and also in the design order k. Now, sort of the more recent development is that this construction turns out to be very efficient in the sense that to get this approximate k designs, we need only a depth that grows logarithmically with the system size instead of polynomial. So this makes it a very efficient way to generate this k designs. Okay, so having introduced this k designs, one of the questions that we were interested in is how do quantum state designs emerge naturally in many-body systems? Because the constructions that I've showed you are just, in some sense, sort of engineered constructions where you get them from random circuit constructions. Okay. So one of the sort of results that was shown in this projected ensembles literature is the idea of emergent state designs. So here, let me consider a very simple scenario where my dynamics contains no conservation law, and I initialize in an infinite temperature state. So by infinite temperature, I just mean that choose a state size such that the energy of this state size matches the canonical ensemble at infinite temperature. So for concreteness, you can think of this Hamiltonian as, for example, this mixed-field Ising model, where it contains the XX coupling and then two magnetic fields along the x and y directions. And this system for typical parameters is quantum chaotic. And here we can choose the initial state to be just the 0 state, which would satisfy the infinite temperature condition. And what was shown in this model is that at late times, if you evolve the system for late times and then look at the projected ensemble obtained by measuring the subsystem B, then it turns out that the projected ensemble on A turns out to approximate this Haar-random distribution in a k design sense, as I've discussed before, where this k here is roughly speaking given by the ratio between the number of qubits in B and the number of qubits in A. So this means that if you increase the size of B, then this would converge better and better to a k design by matching higher and higher moments.
Dariel, sorry to interrupt you. Yeah, I have. So you were talking about these results. So especially this result that you are showing right now, these are not rigorous results, right? Like, I mean, in the sense that, yeah, they observe this, but the analytical results have only been proven in the limit where the NB goes to infinity, essentially, right? Am I right in saying this?
Right. Yes. So maybe I should discuss this in a bit more detail. So for this, of course, for specific Hamiltonian like this, it's very hard to prove that the projected ensemble is a k design for this model. So this is really a toy example. So there are cases where things can be proven sort of analytically. And one of the cases that I want to highlight is this paper by Wenwei Ho and Sumon Choi, where they showed that for a kicked Ising model, so not quite this Hamiltonian, but if you imagine a Floquet dynamics where you have Ising interactions and then kicks in a certain Pauli direction. So if you repeat this sort of periodically, what they can prove is that after a certain time, the projected ensemble can be shown to form k designs. So there are cases where people can prove this rigorously. And for specific Hamiltonians like this mixed-field Ising model, the evidence is mostly numerical. And then there are, of course, also experimental realizations using Rydberg atoms to study this emergence. But I should say that this design order k here, which is given by this ratio of NB to NA, this is actually what you would expect to get from a random circuit construction, just by this cardinality argument. So if you want to form a k design, the number of states that you need in your ensemble roughly grows as like 2 to the k times NA, just from cardinality bounds. So this sort of loosely speaking it's the same kind of result that you expect from random circuit sampling. Yeah. Right. Okay. So having said that, here are some sort of early evidence that this projected ensembles do behave like K designs. So, for example, for this mixed-view Ising model, this has been well studied numerically, and one can see that the trace distance between the projected ensemble and the K and the Haar ensemble at Kth moments. Typically, what it does is it will decay in time, and then you will reach a plateau. And this plateau here is just because of the finite size effects. So as you can see here that if you take these late time values of the trace distance, if it's a chaotic system, it would decay exponentially with the number of buff qubits, B. Whereas for integrable systems, it's independent of the buff qubits, which means that it doesn't converge to a K design. And for and also in the Mano Andres group at Caltech, they implemented a similar model experimentally with Rydberg atoms, and they were able to show signatures of emergent K designs in this system.
Dariel, sorry to interrupt again. There's a question in the chat. The participant is not able to ask some technical issues. They're saying why infinite temperature state was ground state. So why was the infinite temperature state the ground state?
I see. Oh yeah. So good question. So here, this 0 here is not the ground state of the Hamiltonian, right? The ground state of this Hamiltonian is not described by this product states. Now, here, what this infinite temperature means is that you can think of this as two ways. So one way is that you can think of this, one way to get infinite temperature state is by looking at the eigenstates of this Hamiltonian, and then you pick an eigenstate that is close to the middle of the energy spectrum. So that, roughly speaking, corresponds to a high temperature, a very high temperature eigenstate. Now, another way to prepare this infinite temperature states is by preparing in a state, let's say a product state, that satisfies this condition, which means its energy matches canonical ensemble predictions at infinite temperature. And then you apply a late time quench dynamics, so you evolve this for a long time. And we expect such states to behave like infinite temperature states as well. So it's not the ground state of the Hamiltonian. That will correspond to 0 temperature, I guess. Okay. Right. So in a previous work, we have also shown that this projected ensembles protocol turns out to be an optimal way to convert classical to quantum randomness. So in the previous case, what was interesting about the projected ensemble is that the entire protocol is deterministic, right? So the initial state is just prepared in a deterministic state, and the evolution is also fixed. And the only source of randomness comes from the measurement process. So each measurement outcome is random, and that collapses the remaining qubits into some random states. Now, what we showed in this previous paper is that you can think of this as a conversion from classical to quantum randomness just by injecting classical entropy into this protocol. So, for example, you could imagine that the initial state, instead of being in the all 0 states, is sampled from a classical bit string. So those are also infinite temperature states. And or for example, your Hamiltonian could have some random disorder just by adding like random magnetic fields. And that's also another source of classical randomness that you can inject. And what we show is that if I look at the trace distance between the projected ensemble and the Haar ensemble, it obeys this exponential decay as a function of how much entropy, classical entropy, that we inject into this protocol. And then that turns out to be an optimal scaling, which tells us that this protocol for quantum chaotic systems, it's converting classical to quantum randomness.
So this graph, is it a numerical result, or is it?
Yeah, so the data points here correspond to numerical data that's collected from this mixed view Ising model. And then the dashed line here are random matrix predictions by assuming that the dynamics is Haar-random. So the dashed line here is not supposed to be a fit of the data points, so they are collected independently. And what's striking is that the data points here, they basically obey very well to this random matrix predictions.
Okay,
Right.
thank you.
So yeah, thanks for the question. So one way to think about this phenomena is through the lens of quantum thermalization, which is an sort of well-established area of work that tries to connect between an apparent paradox between quantum mechanics and thermodynamics. So as we know, in closed systems, quantum dynamics is unitary and therefore reversible. However, thermalization is a behavior that is typically irreversible, for example, by the second law of thermodynamics. So, of course, the big question that people have tried to study over the years is how does an isolated many-body system that's not connected to a heat bath thermalize? And the resolution to this problem is understood in the sense that you know even though the global state is pure, it's undergoing chaotic unitary dynamics. So which means that the global state itself is actually not described by a Gibbs state. But what we understand is that if we local properties of this system, so if I just look at a sub-region of this many-body system, then the sub-region of this can be well described as if the global state came from a Gibbs state. So this is the idea that many-body systems, even though they are complex and are not described by thermodynamics, they turn out to be locally thermal. Now, into this framework, you can think of
Sorry. So the butterfly, I guess, is like the butterfly effect chaos symbol. Is that what it means?
Right. Yeah. So one of the mechanisms for this is that you get this quantum information scrambling. So local information that is local quantum information undergoing this dynamics becomes scrambled into non-local degrees of freedom. And that's one mechanism that gives rise to this irreversibility on a local scale because the information has delocalized, such that if I just look at the information on a local subsystem, it behaves as if it was a thermal system where information is just lost.
Right. So I was asking a very dumb
Mhm.
question. I was asking, what does the butterfly have to do with it?
Oh
Is
yeah.
it just the
So this is
chaos
supposed to
thing?
represent. Yeah, it's
Okay.
supposed to represent quantum chaos. Yes.
Since you've already been interrupted, I'll take this opportunity to interrupt you once more. So the point, one of the things that interests me about these projected designs is that, can you prove, or is it known whether you can increase the order of design by measurement? So say I start from a state which is close to a K design, then I make measurements get to some K prime design. Can I prove that K prime cannot be greater than K? Or is it possible?
So I think so. Well, so I guess maybe a bit of spoiler. It turns out that if you start from, let's say, K design and then you measure it, you can guarantee that you can obtain K/2 design. And in some sense, that is an optimal result. So you cannot get the final design that's larger than the original K. Yeah, but yeah, thanks for the question. I'll mention this in more detail later on. Yeah. Right. Okay. So one way to think about this projected design or this phenomenon of emergent state design is through what is known as a deep thermalization. So as I described, thermalization basically just tells us that local density matrices of complex many-body systems behave as if it were a thermal state. And deep thermalization, which corresponds to higher moments of this projected ensemble, goes one step deeper. So what it tells us is that the projected ensemble on a local subsystem doesn't just behave like a thermal ensemble, but it also has this feature of being maximally random.
Am I audible now?
Yeah. Come again?
Can you hear me?
Yes.
So I was thinking that this thermalization that you're talking is a probabilistic notion, right? It's not a deterministic statement.
Well, so by thermalization, what I mean is that the local subsystem of this many-body states is described by, for example, the Gibbs states, right, at some temperature.
Only with high probability, right?
Yeah, with high probability, yes.
Yeah, because Popescu sort result is probabilistic. So this deep thermalization is also probabilistic in nature.
Sorry, what do you mean by probabilistic here?
So, like in k equal to 1, I know that if you take a Haar-random state, then with high probability, you can prove that the marginals will be thermal. Like the probability is exponentially high. You cannot say that all the states are thermal.
Yes, and well, this is to be expected, right? Even for thermalization. So when we say that the local subsystem behaves like a thermal state, this cannot be true for any late times because of this Poincaré recurrence. So if you wait for double exponential timescales, then there will be a time in which it basically goes back to being a product state, so it loses the thermal property. But those instances are very rare. So if one wishes to prove, let's say, thermalization rigorously, then this should be done in with high probability at late times.
Yeah, I see. But I thought that this is because you are starting from Haar-random state, so the randomization is coming from there.
Yeah, so I mean, I guess it depends on what's your construction. So if you assume that your dynamics is governed by some Haar-random dynamics, then you can only prove this with high probability that if you sample a Haar-random unitary that describes the dynamics, then with probability that is like 1 minus an exponentially small error, then you can
Right.
guarantee that forms a K design. Yeah.
So for deep thermalization, these results, I mean, these kind of things will carry over, that you will have similar kind of results.
Sorry, could you repeat again?
For deep thermalization also, you will have similar sort of results, right?
Yes, that's right.
Yeah. Thank you.
Yeah, thank you. Right. So what I've described so far is this infinite temperature thermalization, where the local density matrix becomes like a maximally mixed state. So, and then correspondingly, the local projected ensemble is an unraveling of the maximally mixed state that is described by these K designs, which are approximations of Haar-randomness. But one could also ask sort of a more nuanced question. So what if instead of infinite temperature, we have a finite temperature state, and that sort of encapsulates the energy conservation in the dynamics. Or we could also have other constraints, for example, like charge conservation or other conservation laws. Or, for example, we can also have constraints on the amount of entanglement that's generated in the system. So how can we sort of describe deep thermalization in this much more general context beyond the infinite temperature framework? And for that, we need the proper way to generalize beyond these K designs and Haar-randomness. So one thing that I will introduce now is it's a path to generalizing this, known as a Scrooge ensemble. So the idea of Scrooge ensemble is not it's not new. It has been introduced in the context of quantum information theory in the 1990s. And I guess my favorite way to describe Scrooge ensemble is through a two-party game. Which I'll now describe. So suppose we have two players, Alice and Bob. So Alice will prepare states from some ensemble of her choice. So this will be some ensemble that's described by some weights pz and some states psi z. So here, this z here are not necessarily measurement outcomes of the projected ensemble. You can just think of this as an arbitrary label that describes different states. Now, this ensemble is known to both Alice and Bob, so they know exactly which ensemble was being selected for this game. And the density operator for this ensemble is just described by the average quantum state, so averaging over all these weights pz. So this game goes as follows. So Alice would sample states drawn from this ensemble based on a classical label. So she would know this classical label, which is just given by how the states were indexed. And then she would send this corresponding quantum state psi z over to Bob, right? So for example, she could think of some numbers and then prepare some states according to those classical labels. And Bob's job is to apply any quantum measurement of his choice in order to try to recover which classical label was being prepared, right? So the game for Bob is just to guess the numbers that Alice is trying to transmit. So it's a classical information transmission through quantum states. Now, the question here is that given a fixed density operator, of course, we know that there are many ways to represent an ensemble that describes a density operator sigma. So the question that was studied by Josa, Robb, and Wouters in the 90s is that given the fixed density operator, how can Alice make Bob's life as hard as possible, in the sense that which ensemble E minimizes the amount of classical information that can be extracted by Bob through measurement. So this is quantified by this quantity called the accessible information, which tells you how much classical information can be extracted by applying optimal measurements. Now, what they showed in this paper is that this can be minimized by the so-called Scrooge ensemble, or Scrooge because it's very stingy with the amount of information that you can extract by measuring the system. And the Scrooge ensemble turns out to be a very nice, has a very nice simple description in terms of a deformation of the Haar-random states. So if you take the density operator to be the maximally mixed state, and you ask this question about minimizing accessible information, it turns out that the solution to this problem is just the Haar distribution. And I guess that's intuitive because if you have a Haar distribution, then it's very hard to learn the classical label from measuring because the states are all distributed uniformly in the Hilbert space. So now, to generalize this to arbitrary density operator, what they showed is that you can do this by deforming the Haar ensemble in a simple way. So here, phi here is the Haar ensemble. So d phi is the Haar measure. And what you do is just apply the square root of the density operator to this Haar-random states, and then you just renormalize them. And additionally, what you need to do is you need to sort of shift the weights by how much it overlaps with sigma. And you can show that the average state of this ensemble recovers the density operator sigma. So if sigma becomes the maximally mixed state, then this will converge back to the Haar ensemble, and that's the Haar limits of this. Okay, so having introduced this Scrooge ensemble, the question is, well, does deep thermalization in this more general constraint scenarios, are they described by the emergence of Scrooge ensembles rather than just the Haar ensemble at infinite temperature? Okay,
sorry, Dariel, I think you sort of already sorry to interrupt. I think you already mentioned this, but what was the original motivation behind studying these Scrooge ensembles? Looks like a kind of a strange game, right? I mean, it's not very clear to me why how they stumbled upon this.
Right. So I mean, this setup of this two-party game is not new in this paper. So I guess something that's more familiar is the opposite question, that given a fixed density operator, which ensemble maximizes the accessible information? And that's the famous Holivo bound, which describes the ensemble that basically allows you to transmit the most amount of classical information.
I see.
So in this paper, they're asking a sort of complementary question to the Holivo bound.
Yes.
And that's sort of the opposite of the Scrooge. Yeah.
So just to make sure I'm following this properly, if we just flip the minimize to maximize here, this would become the Holivo bound, like the maximum amount you can extract. Is that
right?
Cool. Thank you.
Yes. So the opposite to the Scrooge ensemble would be an ensemble that is comprised that's composed of the eigenvalues and eigenstates of sigma. Right. So if you send the eigen ensemble, then that will maximize the accessible information.
Yeah. Right. Okay. Thank you.
Yeah. Thanks. So, right. So just like Haar ensemble, Scrooge ensembles are typically exponentially complex. So, of course, Scrooge itself, it depends on the density operator sigma. So what was shown in a recent paper by Max McGinley and Thomas Schuster is that if you pick a density operator that has, let's say, low purity, then a typical state that's drawn from the Scrooge ensemble typically would, again, have complexity that's exponential in the system size. So this motivates one to define what is known as Scrooge K-design, which is a parallel to the familiar K-designs in the Haar-random case. So once again, we can define an ensemble to be a K-design, a Scrooge K-design, if it matches the K moments of the Scrooge distribution up to some small error epsilon. Right? And then this K basically quantifies how well we approximate this moments of the Scrooge ensemble. So here's a sort of schematic that as you start increasing K, you start to cover this Hilbert space more and more closely to the distribution of the Scrooge. And then ultimately you end up with this distribution that over the entire Hilbert space that recovers this Scrooge distribution. And it's not a uniform distribution because it's determined by the density operator sigma. So if sigma is the maximally mixed state, then this would be just a uniform distribution over the Hilbert space. But for Scrooge, because there's a sort of a non-trivial density operator, that will give you some asymmetry in the distribution. Right. So here's the
sorry, and so
yeah.
Just sorry. So when you say exponential complexity, is it similar in the sense that like circuit depth is very high or the gate count is very high? Is it in the same sense?
Exactly, yeah. So you can ask like what's the circuit depth required to prepare the Scrooge states? So they have very similar scalings as Haar-random states. So so they are exponentially costly to prepare.
In the exact case, I guess.
In the exact case, yes. So right. So Scrooge designs are supposed to be analogous to just K
the
designs,
approximation,
with low complexity
exactly.
approximations.
Right.
Yeah.
Gotcha. Yeah, thanks.
So, right, thanks for the question. So, the main message of this talk, the main takeaway is that Scrooge designs provide a natural framework to characterize these complex many-body systems under physical constraints such as energy constraints or charge conservation or other conservation laws. And in some sense, the intuition behind this statement is that you can really think of this as two parts to the Scrooge. So there is a density operator sigma, and this is what I say captures the physics of the system, because that basically tells us something about the conservation laws or the constraints that are inherent in the system. And the Scrooge part tells us is that what the Scrooge part tells us is that if I fix the density operator that is just given to me by the physics, then the Scrooge ensemble captures sort of this maximally random distribution that is consistent with whatever density operator that I fix due to the constraints. Right.
So just to check my intuitions, if I put sigma to be, say, like, I don't know, the identity matrix or something, do we recover the Haar-random distribution?
Yes, you do, because d phi here is the Haar measure. So if you set sigma to be the maximally mixed state, then the weights are just given by the Haar measure, and then the states are just the Haar-random states. Yeah.
Gotcha. Makes sense. Thanks.
Right. So in this paper, we're interested in two main questions. The first question is, when can we rigorously establish that Scrooge designs emerge in physical systems? And secondly, can we say something about what are the key physical ingredients for these Scrooge designs to emerge, and when they do not emerge, and what are possible obstructions to this Scrooge formation? So this was captured in this recent paper that we have, and we have and the main results a set of theorems where we can establish this rigorously. So in the first case, let us consider just the late time dynamics on the global system. So here there's no measurements. And for example, let's initialize in let's say all zero states, and then we evolve this for late times under some Hamiltonian. And we want to look at the temporal ensemble. So this was an object that was studied by a previous paper by Mok et al. And one question you can ask is that what does this ensemble behave like at late times, right? So if you just look at these different states that are indexed by times, and you can ask, well, does this ensemble converge to something that's universal? And what we show here is that, assuming some very standard assumptions about the spectrum of the Hamiltonian, called the Cave-No resonance property, then what we show is that the late time temporal ensemble, which is the distributions of the states indexed by different times, they form a Scrooge K design with respect to this diagonal density operator. So this diagonal density operator here, it's something that's more well known in this context of thermalization, where it is just the density operator that is diagonal in the energy basis. So really, you can think of this as a d-phase state in the energy basis. So what we show is that the temporal ensemble that's obtained without any measurements already forms a Scrooge K design with respect to this diagonal ensemble. Here we can only prove this with a certain condition, that this diagonal ensemble needs to be a low purity density operator. So that's quite a standard assumption. And by low purity here, what I mean is that that k squared times the square root of the purity, so 2 here, this represents the Shetland 2 norm. This has to be much smaller than 1. And this also gives us a sense of how well this approximation to Scrooge holds and when it breaks down. So you can think of this as a bound on what's the kth order convergence to the Scrooge given the purity of the diagonal states. Right.
Sorry, so what kind of Hamiltonians does this hold for? Like what are the restrictions on the Hamiltonian? Because what you have done is essentially this temporal ensemble is also like what you see in ETH, right? This time averaged ensemble and what it converges to, right? So what you're showing essentially is that there's this universal sigma diagonal state, and the Scrooge ensemble with respect to the state. When you consider this applied to a K design, this is the state that you obtain at the end. But is it like a universal statement? So can I think that, for whenever ETH holds for a given Hamiltonian, does this also hold?
So this is a bit stronger than ETH. So you can think of a thermalization as just K equals to 1, right? So that usually what this means is
Right,
so
right.
so to get thermalization, what is sufficient is I believe it's K equals to second no resonance or maybe the first no resonance, which means just tells you that level eigenvalues are repelled. So I should maybe mention this in a bit more detail. This K no resonance here, what it says is that if I take any K energy levels from the spectrum, right, the sum of all these energy levels, the sum of these energy levels can only be the same as the sum of any other K levels, if and only if these are the same levels up to permutations, right? So here is a little bit abstract, but maybe if you can think of the case of K equals to 1, what this tells us is that the energy spectrum is a non-degenerate. Yeah. So it's so this no resonance property is in some sense a generalization of this non-degeneracy in the spectrum. Right. And in terms of the Hamiltonian, there's no other assumption other than this spectral assumption. So of course, you can ask whether this is a realistic model of physical Hamiltonians, and I guess for the most part they are. Although it's hard to prove this rigorously for specific many-body systems, but what typical quantum chaotic Hamiltonians have is also this cave no resonance property.
Right, you can prove a typicality statement, like if you sample from the space of Hamiltonians on an average, I think you're almost surely you're going to obtain Hamiltonian which is non-degenerate, like it's simple spectrum, I guess.
Right. So for example, if let's say H is a GUE Hamiltonian, or one of these random matrix models, then what you can show is that a large fraction, except for a small, negligible measure zero set of eigenvalues, most of them obey this cave no resonance property. So there are cases that one can prove, like for example, as you said, typicality, where this can be established. But if you want to ask, for example, like the mixed view Ising model or something that's non-random, then it's usually quite hard to prove this property, although we expect this to be true based on just numerical evidence. Yeah.
Right. Thanks.
Right. So this is so far we have not discussed any measurements. This is just the temporal ensemble on the global system. So the next set of theorems describe the projected ensemble and how Scrooge can emerge in those systems. So
sorry. So before you go on, could you say a bit more about what the condition is? So this kth no resonance condition. I'm getting a little bit confused because I thought EI is the energy at the ith level. So this I understand. You take, I think, the first. I know you index them in whichever way you want. You pick some k of them. That's okay. Well, what is E prime? Is it some different indexing of the same energy levels?
Yeah.
Is that what you mean?
Right. Yeah. So E prime is just a set another set of k energy levels. Right. So for example, what this means is that let's say we just take two subsets of the energy levels. Like let's say you pick k of those energy levels, and this could be independently drawn. So what this no resonance property says is that if the sum of these two agree, then it must be the case that the two sets of energy levels, the k energy levels that you draw are exactly the same set, up to just a reordering of the indices. Right? Yeah.
So kth no resonance means that for all k, these like the size 1 set satisfies this, size 2 set satisfies this, and all the way up to k. Is that how I should think about it?
Okay. Yes, exactly. So it's a hierarchy of no resonance conditions, and I guess the intuitive k equals to 1 is most intuitive because what it tells us is that two energy levels coincide if and only if they are the same energy level, which just tells you that the spectrum is non-degenerate. So let's say k equals to 2. What that tells us is that that energy differences are also non-degenerate. So which means that
Yes.
two pairs of energy differences are equivalent if and only if they correspond to the same energy levels. Yeah. And this is the
Yes.
generalization of that state.
Yes. Okay. Thanks.
Yeah, thanks for the question.
And can it be that in the sorry, I'm taking so much time. It's just about okay. I'll shut up now. But can it be that most eigenvalues in the spectrum satisfy this property except some of them? So you fixed one Hamiltonian, but suppose most of them satisfy this condition except maybe some very high or very low energy eigenvalues. Can we still does the theorem still apply? Is it like robust to these kinds of things, or does it have to be true for all eigenvalues? Is what I'm trying to understand.
Right. Yeah, no, that's an excellent question. So in this paper, we didn't analyze this case that you mentioned where some of these eigenvalues are allowed to violate the no resonance property. But what I expect would be that if as long as the fraction of eigenvalues that do not satisfy the Kth resonance, no resonance is small, then you have an error that is related to the fraction of energy levels that violate this no resonance property.
Right.
And as you mentioned that the case of k equals to 1, this was also recently analyzed, where they showed that that you can have thermalization that's robust, even if it violates some of these non-degeneracy conditions. So you're allowed to have some degeneracies or some resonances in the spectrum as long as there are a small number of them, then you can show that it's robust under such effects. So one question that would be interesting to probe is exactly as you said, like how robust is this to the fraction of energy levels that violate this no resonance? Yeah.
Thank you.
Yeah, thanks. Okay, so now I'll move on to the statements about projected ensemble and when we can see Scrooge emerge in these systems. So here I have a pair of two theorems, which should be thought of as complementary theorems. And just for brevity, I'll call them the so-called 2k to k theorems for reasons that will be apparent soon. So in one way to model this is that, let's say my initial state or the state that it's that I prepare before measuring is some scrambled state. So we can model this as a state that's drawn from some Scrooge 2k design, right? So suppose I have a state that's drawn from a Scrooge 2k design, and I look at its projected ensemble by measuring B, and you can ask, what does this converge to? And I should mention that this psi here is not averaged over the Scrooge ensemble. It's a fixed state that is sampled from this Scrooge distribution. But once you sample it, you fix it throughout the experiment. And here we show that the projected ensemble that's obtained from this state psi generally forms a mixture of Scrooge K designs for assuming again this low priority condition. And here you can think of this as a mixture for every measurement outcome Z. So I'm defining this sigma A condition on Z just by looking at the global sigma for this Scrooge. So sigma here is supposed to be the sigma of the initial Scrooge ensemble. And for every measurement outcome, I can project this onto the measurement outcome Z. And that describes the density operator on A. And what I'm saying here is that the projected ensemble behaves as if it were a mixture of Scrooge K designs, where all these where we have one Scrooge ensemble for every measurement outcome. So this is a pretty generic behavior, but of course physically we don't expect this mixture to be exponentially sized because the number of Scrooge ensembles in this mixture is the same as the number of measurement outcomes, which is like 2 to the MB. But in physical systems, we expect this to collapse to just a polynomial number of them because you can have the case where this sigma A condition on Z they're not all mutually different. So in the case where, let's say, some of this, well, in the extreme case where, let's say, all these conditional mixed states are independent of the measurement outcome, then what this theorem tells you is that the projected ensemble collapses to a single Scrooge ensemble. But in general, we can describe them by this sort of mixture of Scrooge. Okay, yeah, I should mention that in the Haar limit, if I just take sigma to be the maximally mixed state, then what this tells you is that a state that's drawn from a 2K Haar design will produce a K design in its projected ensemble. And this was a result that was studied in a previous work by Ghosh et al. And I guess there was a previous question that asked about a design starting from a K design state. So this is a sort of the Haar limit of that statement, which is saying that a 2K design will produce a K design in its projected ensemble.
But
Right.
sorry, does it? You mentioned something about optimality as well. I didn't fully understand. So here you're showing existence. How is it also true that you can't do better than K by 2?
Oh. Yes. So well, that's supposed to be the next slide, but I'll mention it now.
I see.
So this is optimal in a sense that if let's say if I have K equals to 2. So what this theorem tells us is that a 4 design is sufficient to prepare a 2 design projected ensemble, but a 3 design is not. So if I have a 3 design, I cannot guarantee that the projected ensemble will always be a 2 design. And in fact, there are explicit counterexamples that one can construct such that it doesn't produce a 2 design. Yeah.
I
So
see.
in some sense, this is optimal
for integers, basically.
Yeah. Right. So this is one model in which we can prove that Scrooge emerges in the projected ensemble, where the global state is assumed to be drawn from some Scrooge 2K design. And a complementary sort of viewpoint is that we can have the case where the initial state size 0 is an arbitrary entangled state between A and B. So it doesn't have to be highly complex or maximally random. So it's just some entangled state. And what we do to it is we apply a scrambling evolution. And what this sort of does is it scrambles the quantum information shared between A and B into non-local degrees of freedom. So for this theorem, what we do is we assume that UB here is sampled from a unitary 2K design. And then we measure the buff qubits again and look at the projected ensemble. And here we show that the projected ensemble forms just a single Scrooge K design with respect to the reduced density matrix on A. Right, so again, this if you want to think of this in the Haar limit, you can interpret this to mean that if I have a maximally entangled state between A and B, and I apply this scrambling evolution given by the unitary 2K design, then the projected ensemble would form a K design in the usual Haar sense. And this theorem generalizes beyond that statement. Right. Okay, so I mean, these are sort of rigorous statements that tell us when this Scrooge will emerge. And here next, what I want to do is to provide a bit of physical intuition about what's the meaning of these theorems. Right. So.
I'm sorry. There's a question in the chat. Should I read it out? Is that okay?
Yes, please. Yeah.
So the question says, this. Okay, I'll just read it out verbatim. Okay, so then we'll see what it means. This no resonance condition clearly fails for non-interacting Hamiltonians, but that is okay. I was wondering if K is related to Hamiltonian being at least f of K local, where f is some reasonable function.
I think that's it. I think that's not sufficient. Like if you have an interacting system, it doesn't always guarantee that the cave no resonance is satisfied. And so the cave no resonance is of course it's an assumption about the spectrum. It's loosely speaking, it's saying that the spectrum behaves like a generic eigenspectrum. So for example, like the spectrum that you get from random matrices, but it's not a statement that's true for any interacting system. And I guess that's where the assumption of chaos lies. So this is not true for any. Here when I say global Scrooge from chaotic dynamics, of course, I'm not defining chaos in any proper sense of the word. But sort of the chaotic assumption boils down to this spectral assumption about the Hamiltonian. So it's not true for any interacting system. Yeah. Right. So yeah, if there are no other questions, maybe I'll get into sort of the physical interpretation of the 3 theorems. And if you just
so you're not doing the proofs?
Oh, Yeah, I don't think I would describe the proof, but well, I can roughly,
Okay, fine.
yeah. Well, the proofs are slightly technical. Let's see.
So it's fine, sir. Please carry on.
Yeah.
I was just
Okay.
sorry.
Yeah. No, you can ask me about questions about the proof, and I'll be happy to chat about it later. Yeah. Right. So if you sort of view the two theorems, 1 and 2 together, what this tells us is that the projected ensemble obtained by a late time evolution does form a Scrooge design. So recall that theorem 1 tells us that late time states form a Scrooge design with respect to the diagonal ensemble. And then theorem 2 tells us that if I start with a state that's sampled from a Scrooge design and I look at its projected ensemble, I'll get a K design, a Scrooge K design. So this is in some sense, a statement about deep thermalization. And the next thing is that, and yeah, this is related to the question that was asked just now, is that this 2k to k is optimal. At least we know this for the case of k equals to 2 because of this explicit counterexample. So for example, if I have stabilizer states for psi, or let's say ub here it's a Clifford unitary and psi 0 is a stabilizer state. Now in both of these cases we have exact 3 designs. But one can show that the projected ensemble here does not converge to a 2 design. In fact, it only converges to a 1 design. And the meaning is because it has no magic. So what this also tells us is that magic is necessary for Scrooge to emerge. And in the absence of magic, that will obstruct this emergence of Scrooge ensembles, even though the global state can be a good approximation of this Haar dynamics. Okay. So having said that, the sort of next question that we are interested in is not so much about the theorems, but rather what the physical ingredients are necessary for this Scrooge to emerge. And in this paper, we identified 3 sort of quantum resources that are needed for Scrooge to emerge. And in the absence of any of these resources, or if they are insufficient, then we can show that there are examples in which the Scrooge can be shown to not emerge. So I guess the first one is the case of magic, which I've just described. So in the absence of magic, for example, in stabilizer states, what we can show is that the projected ensemble is not a Scrooge ensemble. Now, the second resource is about scrambling, or in some sense, entanglement. That if the information shared between A and B is not sufficiently scrambled, then there are cases where we can show that the projected ensemble is not given by the Scrooge ensemble, which tells us that scrambling is again a necessary resource for this. And sort of the last physical resource that we identified is this resource of coherence, which is the sort of the strength of the off-diagonal matrix elements in the computational basis. So, for example, we can consider this set states called subset phase states. So these are states that are just random superpositions of this computational basis states. And you can sort of understand this by saying that if there's insufficient coherence in these states, which you can tune by choosing how you construct these superpositions, then there will be cases where the projected ensemble obtained from such states are not described by Scrooge. And in fact, there'll be a phase transition after which you can show that the Scrooge will emerge. Okay, so these are just quantum resources that are necessary for Scrooge. And here I'll demonstrate this through some numerical examples that hopefully will make this point clearer. Okay, so sort of one system that we simulate that gives us a nice way of handling these quantum resources is this construction known as doped Clifford circuits. So in this circuit, what we do is we apply a round of Clifford unitaries, and then we apply T-gates. So basically, it's a Clifford circuit that's doped with T-gates. And we have essentially 2 parameters that we can tune here. One is NT, so that's the total number of T-gates that's injected into the circuit. So that, roughly speaking, controls the amount of magic that we inject into the system. So the more T-gates we apply, the more magical we should get. And the second thing we can control is the number of layers, so how many times we repeat this circuits. So this D here, roughly speaking, the larger circuit depth we go, we'll have more entanglement generated in the system, and there's also more sort of scrambling that occurs. So you can think of this as a two-parameter family of circuits, and one of them controls the magic and the other one controls the scrambling. Of course, it's not so precisely delineated that way because both NT and D do control both magic and scrambling. So it's not exactly true that one of them is solely controlling the magic and the other one is the scrambling. Right, but nonetheless, what we can see is that if I want to achieve Scrooge-K design, so here this is measuring the trace distance for the second moment. And if I want to achieve Scrooge-K design, what I require is both the number of T-gates and the circuit depth to be large. And in the absence of one of these, here we can see that they do not form Scrooge behavior. Right, and on the right here, you can just see that as a function of T-gates, the number of T-gates, the trace distance decreases exponentially, with the system size. So this is what we expect from injecting magic into the system. Okay, so that's one example. And right, so the second example here is about the resource of coherence. So one nice model that allows us to tune the amount of coherence in the system is this idea of commuting quantum circuits, or also known as IQP circuits. So in this case, we initialize the system in a plus state, and we apply a random diagonal unitary to scramble the information. So such states have a high magic and also high degrees of scrambling. And what we can do is we can apply a small rotation about the y-axis. And this really controls the amount of coherence that we inject into the system, and followed by measurements in the z-basis. Right, so here I'm plotting, again, the trace distance with respect to the Scrooge-2 design as a function of this rotation angle. So if I do not rotate this system, then this gives you a case where the projected ensemble is, in fact, not a Scrooge design. It's far away from a Scrooge design, even if the number of buff qubits is very large. Right, but on the other hand, if I have just a little bit of rotation, it turns out that that will give you a phase transition that's due to this injection of coherence. And this is what is known as a coherence-induced deep thermalization, where injecting coherence past a critical point allows us to achieve a phase transition in which the projected ensemble converges to a Scrooge ensemble. Right, and then for the last example, this is the most physically relevant example, I would say, where here we look at 1D ground states of integrable systems. So this is intentionally chosen such that they're far away from quantum chaotic regimes, where we look at ground states. So these are low energy states, and they are also integrable Hamiltonian, so which means they obey area law scaling for the entanglement. And one prototypical example is the case of the transverse field Ising Hamiltonian. So this is just a quantum Ising model, which is known to be integrable. So in this case, we start from the ground state, psi 0, of this Hamiltonian, and we apply different choices of the unitary to the buff qubits before we measure them. And here again, there are several choices we can make. For example, if we just do not do anything to the buff qubits, that corresponds to the identity operation. And here we can see that as a function of the magnetic field H, the trace distance is quite high. And now we can start to add more complexity to this. So for example, I can apply a single qubit Haar rotation to each of the buff qubits. But now in this case, you also see that the trace distance is high, because this is a non-entangling operation. So it injects magic and coherence into the system, but it doesn't induce entanglement and scrambling. So that's why the trace distance is not decreasing. On the other hand, if you apply a Clifford unitary, a random Clifford unitary here, this gives us a dip in this trace distance corresponding to the quantum critical points. And as baseline, we can construct a simple case where the dynamics is just globally Haar-random. and that gives you sort of a baseline for the trace distance. But what's more interesting is not this particular values, but how they scale with the system size. So we can see that apart from the identity and the local Haar case, both the Clifford and global Haar unitaries exhibit this exponential scaling with respect to the buff size, and of course at different exponential rates. But nonetheless, what this tells us is that in the thermodynamic limits, applying a Clifford unitary to the buff qubits at the critical point gives us a deep thermalization to the Scrooge ensemble. And if we analyze this finite size scaling for this choice of this Clifford unitary, we observe that this obeys a phase transition at the critical points of the Ising model. And sort of the interpretation of this result is that this is due to the injection of the magic of the ground state. So what I mean by magic is this, that the Clifford unitary itself, by definition, doesn't induce any magic. But we know that the ground state of the transverse view Ising model has a spike in the magic at the critical point. And that spike in the magic corresponds to a spike or a phase transition in the deep thermalization of this ground states exactly at the quantum critical points. Okay, so I mean, there are all these examples that we show, but what they sort of tell us is that there are three necessary resources for deep thermalization, namely magic, scrambling, and also coherence. Okay. Yeah, just to summarize, so in this work, we have proposed Scrooge-K designs, which are low-order approximations to the Scrooge ensemble. And we show that this can arise in a multitude of physical contexts, for example, from late-time dynamics, or also from projected ensembles. So these are different cases where we can show that Scrooge emerges. And furthermore, we have quantified the necessary resources and studied when the Scrooge ensembles emerge and also when they do not emerge. Now, in terms of sort of future directions, there are sort of two classes of questions which I think are quite relevant. So the first one is that these statements are all very general, right, in terms of like 2K to K designs. And sort of one thing that we hope this would allow us to quantify are new physical settings where Scrooge can be shown to emerge. So for example, there could be a class of mechanisms where we observe deep thermalization, and those can be accounted for by this 2K to K theorems. Now, the second sort of more interesting direction, which is a direction that we're working on now, is how can this sort of Scrooge-K designs be applied in quantum technology such as benchmarking and learning applications, analogous to how Haar-random states and K designs have been very useful in the context of this quantum information task. So we believe that Scrooge ensembles can also be used for that purpose, and it's a direction that we're working on at the moment. Yeah. So with that, thank you for your attention, and that's the end of my talk. And I'm happy to take questions and discuss. Yeah, thank you.